Alright, so I want to solve one more problem on metric because I noticed this in one of the past questions and I don't know, so I found it interesting. So we have this question. We are given a metric d which is defined on non-empty set x. So we want to show that this function rho is also a metric. So now remember, what are we going to do? Show the four axioms. So the first one will be 0 less or equal to rho of xy, which is less than infinity. Remember, we have been given that dxy for every xy in x is a metric. That means d actually satisfies all the four axioms already. So I don't know if you want me to write it down. So 0 is less or equal to the xy less than infinity. Then the 2, we have the xy is actually equal to 0 if and only if x equals y. And the third one, the xy is actually equal to the yx. And the fourth one, the xy is less or equal to the xz plus dzy for z in x. So alright, so that shows using this first one, 0 less or equal to the xy. So we know that the xy is actually less than infinity, right? So we know that 1 from the xy less than infinity, we know that 1 plus the xy will also be less than infinity, right? The xy is a distance, right, which is not infinity, it's not equal to it is less than. So you add 1 to the distance, which is a real number, right? It is less than infinity as well. So if you have this, then you divide each one by a real number. This is a real number. So if you divide each of these by this, you have 0 divided by 1 plus the xy. Remember, the xy is not 1 plus the xy is not equal to 0, right? Because the xy, even if the xy is equal to 0, 1 plus 0 will give you 1, right? So remember, the denominator can never be 0. So this is defined. So you have to be careful before you do this. But since it is defined, we are good to go. Alright. So if you do this, 0 divided by this will give you 0. And remember, this function is a rho of xy, and infinity divided by a real number will still be infinity, right? So this satisfies this first axiom. Alright, the second one, right, will be rho of xy equals 0 if and only if x equals 0. So what's the rho of xy? dxy over 1 plus dxy equals 0. And this implies what? You can cross multiply, right? So this times 0 will be 0. This times 0 is 0. Remember, this can be 1. So dxy equals 0. And when is dxy equal to 0? So it says dxy is equal to 0 if and only if x equals y. So this is if and only if x equals y. Then we're good to go. The other way, right, will be only if x equals y. So if x equals y, we have that what? The xy is equal to 0. The xy equals 0. Now divide both sides by the xy. 1 plus the xy. Remember, again, this is not equal to 0 because the xy is, we don't even, the xy is 0, but 1 plus the xy is now non-zero. So we can divide that by this. So this is still 0, and this is the rho of xy, which is 0. Then we've gotten our axiom 2. Then axiom 3 says the distance from xy is actually equal to the distance from y to x. And what is rho of x to y, which is dxy over 1 plus dxy. This is trivial, right? Because dxy, since d is a metric, this is same thing as yx, and this is same thing as dyx. So this is rho of xy, and this is rho of yx, which is actually equal, right? For the fourth axiom, all right, which is this. So how do we show this? So let f of z to be actually z over 1 plus z, okay? Then we claim that this is increasing on 0 infinity. We will see the reason why we need this. This is open bracket. So if we want to, because now we have this, right? If we let z to be the xy, so that shows f of the xy equals the xy over 1 plus the xy, right? So that is why we are having that kind of expression. And we just let rho of xy to be equal to f of the xy. So that, right? So that we need what? Rho of xy to be equal to f of the xy. And we know that the xy is actually what? We want to check now if this is actually true. The xz plus the zy. We cannot just write that because the xy satisfy this. We can't just write it, right? If this happens, then we can have rho of xy. Oh, sorry. This we need to check for if this is actually less or equal to. So not this. This is actually right because the xy is less or equal to this. So we have to check if this is actually less or equal to f of the xz plus f of the zy. So if this happens, then we can have our rho of xz plus rho of zy. So, but for this, we are not sure, right? But we claim that f is increasing. Then if f is increasing, then we can apply this, okay? Because this is less than this, right? Because this is less than this, then we can if this is less than this, it shows that f is increasing, right? So when we say f is increasing, you have f of z to be z over 1 plus z. So you can do this in two ways, I think. You check if this function is increasing, and we said is on 0 infinity, so z is not equal to 0, right? So let's say f1, this is 1 over 2, f2, this is 2 over 3, f3, this is 3 over 4. You can see that f3 is greater than f2, f2 is greater than f1, so that shows f is increasing. If that is not certain, the best approach, you can find the derivative of z, and if the derivative is greater than 0, here remember it is not equal to 0, right? So if it is greater than 0, then we say it is what? It is increasing, strictly increasing. So if it is less or equal to 0, monotonic increasing, like it can be equal to 0, but it is not negative, right? So the derivative now will be 1 plus z, that is v du minus u dv, right, over v squared. And this will give you what? 1 plus z minus z over 1 plus z squared. this is 0, this is 1 over 1 plus z squared, and this is greater than 0, right? This cannot be equal to 0. Squared greater than 0, 1 over something greater than 0 is greater than 0. So the derivative is greater than 0, which is what? Which is strictly increasing. Alright, so since we know f is strictly increasing, now what we need to check is if f of a plus b is actually less or equal to f of a plus f of b. This is what we want to check. Alright, remember f of z is z over 1 plus z. So f of a plus b will be what? A plus b over 1 plus a plus b, right? Now this is same thing as a over 1 plus a plus b over 1 plus a plus b. We separate them. This is less or equal to what? A over 1 plus a. Remember, f is increasing, so this will be greater or equal to this, plus b over 1 plus b. Remember, 1 plus a is less or equal 1 plus a plus b. So if b is 0, then these are equal. If b is non-zero and it is positive, then this is less than 1 plus a plus b. Remember, we are dealing with from 0 to infinity, so that shows it is non-negative. A, b, they are non-negative. All right, if you find the reciprocal, so 1 plus a will now be greater or equal 1 over 1 plus a plus b, right? Because if you have 2 less than 4, now 1 over 2 should be greater than what? 1 over 4, right? 1 over 2 is 0.5, and 1 over 4 is 0.25. So that is the property for reciprocal. All right, so we have this, so that makes this, and a is positive, remember, so the sign remains the same when you multiply. So when you multiply through by a over 1 plus a is actually greater than a over 1 plus a plus b, which is the same thing on this other side. So that shows this is right. And what is this? So this is actually f of a plus f of b. So we've shown that f of a plus b is less or equal to that. So this implies that our rho xy is less or equal to rho of xz plus rho of zy, right? Because a plus b is what? A plus b is the xy, and a will be this f of a plus f of b, right? So this is a plus b. So f of a plus b is actually less or equal to f of a plus f of b, which is what we've done here. And now we can conclude this. Alright, so proved, and I hope you understand this. You carefully study this and you will realize this is actually simple. Thank you. Let's move to the next video.